We're back. The final activity for chapter 6. We're going to talk about glycol formation. Glycol, aka, first of all, what's aka stand for? Also known as vicinal diol. Vicinal is a word that we're supposed to know already. I know some of you haven't reviewed it yet, but it just means on adjacent carbons. Diol is pretty self-explanatory, right? What functional group we talking of, and how many? 2 alcohols on adjacent carbons. So when you see a reaction that does that, the chemical, you're responsible for anything I write here. So if it wasn't on the original, you need to know it. So 6.3a, the chemical you need for glycol formation is this one. O with a little s. Do not put a big S there. That would be oxygen and sulfur, totally unrelated. This is called osmium. Osmium. This is the oxidation state that sets a new record for you. I do not believe in Chem 141 you ever went that high. What does VIII stand for? +8. And the drawing says that, right? Each bond to the more electronegative O gives a +1. There's 8 of them. So you already knew it was osmium 8. Here's some sad news. A lot of chemical companies, because they use chemicals so frequently, they want a better, simpler name. You try that in Chem 141, they just say you get a 0. You've mixed up your nomenclature systems. You're not allowed to use prefixes for ionic compounds. That's only for covalent compounds. You remember those prefixes? Mono, di, tri, tetra. Tetra. You're not allowed to do that, but that's its trade name. So we have to go with it. Okay, and what happens there is you get an intermediate that you're responsible for being able to draw. Intermediate. And you copy all the carbons, but don't copy the pi, because all chapter the pi's been disappearing, right? And the new stuff will be in blue. Do not put a big S there by mistake. You know why I'm going to go nuts if you put a big S instead of a little s, right? What are you saying if you put a big S instead of a little s? Yeah, oxygen, sulfur. Unrelated to this entirely. That's osmium. Okay. Mechanism. You're responsible just for this one step. And it's just 3 arrows and done. It's kind of like hydroboration plus 1 arrow. And it's quite a simple little mechanism. We're attacking an O, and you say, wait, why did you attack the more electronegative atom? This is the first time we've ever done that. And you'd be right. You should have a concern right now. This is the only time we're attacking the more electronegative atom. It's because osmium is +8. How do you get from osmium to osmium +1? What do you have to do to the atom to make it go from 0 to +1? Remove an electron. Remove another, +2. Remove another. Can I go all the way to 8? You've removed 8 electrons from this. It wants them back. It didn't mind the first 5 or 6. When you got to 7 and 8, osmium said, I need my electrons back. I want electrons. I'm pulling on electrons. You have artificially made osmium very, I don't want to say it, but I'm going to say it. It's electronegative because it's got a high charge. If you have a high plus charge, doesn't that make you pull electrons towards you? Isn't that the definition of electronegativity? Until now, you believed it was only the nature of the nucleus, right? And that's true. Until this day, it was just only about the nature of the nucleus. I'm telling you now, when you make things more oxidized, they become more electronegative. They want electrons more. Okay? So that's just so you remember that this is the weirdo. The weirdo. The only time you're attacking a more electronegative atom is here. Okay? And here's the result. Here's how osmium got its electron. Oxygen reluctantly gave up that pair to osmium. And then this guy goes back to which carbon? It's been the same answer every time I've asked that question. The more substituted carbon. And that gives the result. It's a syn addition, isn't it? How do you know? Did you see a set of arrows to make a triangle, then a backside attack? No. Did you see both of the bonds to the carbons happening at the same time? Yeah, they're there. This first arrow made a bond to the end carbon, and this last arrow made a bond to the second carbon. Same time means they both be on the same side, and look, they're on the same side. They're both on the right side there. This is called an osmate ester. Why do we call it an osmate ester? I thought esters came from acid. They do. They do. Osmate esters come from osmic acid. Osmic acid has the same Lewis structure as which acid? Now I do want you to mess up with the cases and get rid of one of the letters. Put a big S in the middle and get rid of the O. That's sulfur. That's sulfuric acid you just drew. It's called isoelectronic with sulfuric acid. Things that are isoelectronic have the same Lewis structure. You did a lot of those in 141, right? Maybe. Osmic acid makes what kind of esters? Osmate esters. Carboxylic acids make carboxylic esters, or carboxylate esters if you want to be consistent. That's the normal esters, right? This thing's unstable. It will break down with this guy. Name that. If you know how to name this, then you know how to name that. And you name this today. Hydrogen peroxide. Well, this one has two groups. One of them's hydrogen. It goes tert-butyl is the other group. Hydrogen peroxide. And what happens is you get this. And what's the name of this functional group? Say it again. Vicinal diol. Also known as, he said it, he said both. Very impressed. Glycol. Yeah. You want color coding? Why not? You also made this. If I write this down there, it sounds silly, but it helps you remember something. Why would I write meow? What animal says meow? Cat. First three letters of cat, also the first three letters of a catalyst. Catalyst is used but not used up. Do you see how you used OSO4 in the first step? Do you see how you remade it in this last step? That's a catalyst. It never gets used up because every time you use it, you remake it. Okay? And I write meow when I remake my catalyst. It's a thing I do. I'm probably the only guy here in the world. I don't know why. Yes? This cannot be a carboxylic acid. If you think it is, you're going to get -1 on your test. Why? Because this would have to be a carbonyl, and now it has 5 bonds. And you're going to thank this man for asking that question later, because on the test, it often shows up like this. CH3, 3 times COOH, and students really think it's the carboxylic acid now. They really do. They're almost like, how can you not think that's the carboxylic acid? Then you realize this thing has 3 methyls on it. It can't have any more than 1 bond extra. There's only 1 bond to O. Can't be a carbonyl. It has to be a peroxide. So, there you go. I'm going to point out something else. Owl doesn't like that chemical. Owl uses NaHSO3 instead. Sodium bisulfite. Okay? And you can use it instead on tests as well. I do not mind. All right. So you should be able to draw the osmate ester given these 2 species. You should be able to give me the 3 arrows to get from this to the osmate ester. 2 things you're responsible for. Third thing you're responsible is knowing the chemical that breaks this back down to that and either the meow or whatever this becomes. I don't even need to see the meow molecule. It was already on the page. I don't need to see it again. So what are the things you need to know? I'll go through them again. You need to know that alkene is going to react with OSO4 to give an osmate ester. You need to be able to draw the osmate ester. It's in a box. That means you should be able to come up with that. Any curved arrows that I draw here, you are supposed to be able to come up with on your own. That's 2. 3, can you tell me the chemical that's going to break this down to the vicinal diol? That's all I need. You can give me either this chemical or this chemical. I don't need anything more than that. Okay? So that's all you need to know. And we didn't do the actual question that was on the page already. Oxidation states were originally -2 for 1 and -1 for 2. Hi. And they ended up as, we can do them down here, a -1 here and a -2 here, a 0 here, sorry. And this was 2, yeah, 2 was in, blue was 2. And 2 is the one in the middle. What do you call that? Going from -1 to 0. Oxidation. Purple, no, yellow we used, yellow. 1 goes to 1. We have -2 going to -1. Also, vicinal diol formation is an oxidation. Both carbons got oxidized. Okay. This is a very good question. What's getting reduced? I'm very happy to hear it. I would have been even happier to hear it here when I said this reaction is called a reduction. She needed to ask that question as well, or somebody, what got oxidized? Because she remembered correctly that you can't have a reduction without also having an oxidation. Organic chemists are a different breed. They only talk about what happens to the organic molecule. So that's why I didn't talk about oxidation. But I want to remind you that H2 had an oxidation state of 0. H bonded to H. Use your rule. When you're bonded to the same electronegativity, what do you get for that? A big fat 0. H in any of these molecules, when you're finished, is +1, whether it's bonded to the more electronegative carbon or the more electronegative oxygen. Every H on this page is +1 except for H2. So what do you call it when you go from 0 to +1? Oxidation or reduction? Oxidation. There is the atom that got oxidized. Next one. Finally going to get around to your question. What atom became reduced? Well, when you made this, osmium is now +6. And it started +8. What do you call that? When osmium goes from +8 to +6? A reduction. That answers your question, doesn't it? During that step, when these two carbons got oxidized, the osmium itself got reduced. Okay? Redox. And then I got to cut to the chase because we're running out of time. The only thing, 2 things you're responsible for ozonolysis. 6.3b. Here they are. 6.3b. One exercise is going to have you doing stuff like this. And you're going to go with O3 excess. And that's step 1. Step 2, sulfur with 2 methyls. You're responsible for those chemicals. I'm going to put them in a box. You should be able to tell me those chemicals if they're missing. And the easy part is telling me the result of this reaction. I'm going to do it this way so that you can tell me how you predict ozonolysis products and there's these little plus signs. I won't be able to move that. It's supposed to be plus signs because there are 3 products. Those are not charges, okay? The reason I wanted the O's close to each other is, can you tell me why? Remember, I'm trying to teach you how to learn this stuff. Watch the video carefully. How do you predict the products? You get your fattest eraser. What did I do? I broke it. What does lysis mean? Yeah. Breaking. Ooh, sit. I don't know how that happened. And what do you put on the end of each pie? I mean, look at the products, people. You keep the beginning of the pie and the end of the pie, but now they're separate places, and they're pies to oxygen now. Did that visual work for you? Because this is what I got on the right side, isn't it? Isn't that what I drew on the right side? How did I get there? I erased the double bond, put an O on each half. That is one. I got back to sit. She asked the question, how does it happen? Now that is an intermediate level organic chemistry mechanism. I love the mechanism, by the way. I love it a lot. But I mean, we did one that's harder, hydroboration oxidation, but I don't want to keep adding to that list. Okay? So it's just a little advanced how it happens, but it's one of the coolest mechanisms ever. Yes, sir. No, the only part of the mechanism for the first reaction you're responsible for are these 3 arrows and being able to draw the intermediate. And then is the tertiary butyl hydrogen peroxide, is that always the chemical? No. If you're owl, you would prefer using this chemical. You use one or the other. That's entirely up to you. But watch out. I might provide one and ask you what's the product after that. So you can't say, oh, I'm going to learn only this one or only this one. But I'll tell you, I'm not going to put NaHSO3 on your test. I'm going to stick with the ones we did in the lecture. Okay?
What would the product?
I'll make it into a test question right now. You ready? I'm going to make it into a test question. What chemical do you provide me with to create this? And, well, I didn't draw it right. Black, 5 carbons. Vicinal diol. So, on a test, if I have this, can you tell me what chemical is going to break it down to this? I want either this in the box or this. Okay? That's what you're responsible for. So I'm going to go with the tert-butyl hydrogen peroxide because that breaks it down to give me this. And I don't care. You don't have to show me the ozone. Osmium. I don't need to see the osmium. It's a side product. Okay.
So we don't also have to know the mechanism of how tert-butyl.
No, that is a very complicated mechanism as well. A lot of inorganic redox going on there. So there's a big mechanism, but you're only responsible for one little piece of it. And down here, no pieces. Okay. So the only 2 things I can ask here, if I gave you this and these 3 products, could you tell me what to put in the box? Or if I gave you the molecule and these reactants, can you predict these 3 products? That's the 2 things. That's it. End of chapter 6. End of story. And I'm not going to go through the redox exercise again, but these are even more oxidized carbons. Each one of them has one more bond to O. So each reaction here was redox, or oxidation for carbon. It's a big time oxidation. And we had a question over there.
Yeah, one more question. So no, you need the hydrogen peroxide, but is the tertiary butyl part of it subject to change?
It does change, yes.
So
Those O's end up attached to the osmium right here. I was trying to show that here. There's the O's from the tert-butyl hydrogen. You don't have to know which O either.
Would it ever be like isopropyl?
No, it doesn't work that well with that one. He's asking, can you change the tert-butyl group? I'm going to tell you, if you give me any peroxide there, I'm going to give you at least partial credit. Any peroxide. If you put hydrogen peroxide there, I'll probably give you 3/4 of a point. It doesn't work well with alkenes because solubility issues, but that's a lab issue more than a lecture issue. I need a peroxide. That's what I want. And this one, if you're curious about where the 3rd O went, some of you might be, it ends up here. Right there. That's a side product. I don't need it. I need these guys. Be able to predict these prods, not this one. It forms, but it's not really important. That is the word this. Okay. Down here, I just told you how to get it with an eraser. I hacked up this molecule and put the O's on. And that's the end of 6 for us. We're out of here.
What